All right, hello everybody. We are now we've completed a few sessions here so far. We're now moving into a different set of problems, right? So if you guys remember, we were given a new data set of health care data, and we're trying to predict heart disease in patients. And just to recap previously what we have done so far, we have gone so far, we've built some models where the target is continuous. That is the regression space. And then when the relationship is unknown, when the relationship is known to be linear, then we can go down linear regression. If it's unknown, then we go down decision trees. And then we try to improve the performance by combining decision trees randomly, or by combining them sequentially using gradient descent to get gradient boosted trees. This time, we're going off on a different branch where the target is discrete. Okay? So let's go ahead and get started. As usual, let us go ahead and start up pull the data in. So let's go ahead and initialize our libraries first. Typical libraries we have. We've got pandas and let's also bring in the test split, model selection. Okay, we'll bring in the other libraries as necessary. Then data. By the way, whenever you get warnings like this, you might need to update some of the libraries if necessary. Or sometimes some of the updates you actually don't want. You want previous versions, then you can. There's little snippets of code you can write to ignore the warnings. Okay? Not that you should ignore them. You should probably update your code to handle the new libraries. All right, so we're gonna bring in the data, call it df heart, and read CSV, go to the data folder, and then disease and heart disease. All right, so let's see what that looks like. Okay, so this is what we see. Let's look at some of the descriptions of the data. So we have, let's go through one row. So we've got a 63-year-old patient. One second, let me see if somebody else joined, which is why. Okay, all right, so we have a 63-year-old patient. One is male, so it's a male 63-year-old patient. Different types of chest pain. This is the resting blood pressure. I think it's in millimeters, Hg. Then you got cholesterol. And then you have the fasting blood sugar, the resting ECG. This is the maximum heart rate achieved. And then you've got exercise-induced angina. Then you have exercise related to rest. And then these are some calculated values, which is the slope of the peak, the number of vessels colored using the fluoroscopy. So I'm just going through the descriptions of each one of them, right? And then this is the different levels of defectiveness. I think that it goes all the way down to a value of 7, I believe. And then the target, right, which is 1 if the patient was diagnosed to actually have heart disease and 0 otherwise. So anytime we get data like this, first of all, this data is very clean. It's very unlikely in real life you're going to get data like this. But when you know that your target, what you're trying to predict, previously we had prices, house prices, tips, things like that. They're continuous. This time it's discrete. So first of all, you would want to figure out what are the different values that the target can take. Is it just 1 and 0, or is it 1, 2, 3, 4? Maybe 1 means stage 1, 2 means stage 2, 3, 4, something like that. So you can have different values here, but you would like to do some sort of basic analysis on these, right? So remember previously we were doing the dot describe, so we could do that here as well, look at ranges and things like that. But today we have a lot to cover, so I'm going to assume that you guys would do the descriptions, look at the statistics, see how much data is missing, fill in the missing values. So think about it. If you had missing values, you may want to fill it, not either ignore, if a column has many empty values, then you might ignore the entire column. But if you have some patients where not much of the data has been collected, you might drop those patients. But if you have some, that most of the other data is available, just a few are missing, you could consider, doing a forward fill, or imputing that data point. But realize that a good value for doing imputation here would probably be something like the mean, or something like that, right? Because you don't want to replace it with zeros. You definitely don't want to replace it with a forward fill or backward fill, because that doesn't mean anything. There's no relationship between patients. So that type of imputation makes sense. So I'm going to assume that you've done all of that and the data is already cleaned up. Okay. So one thing that is useful for us to know is, okay, we want to figure out what qualifies people to be diagnosed with a certain type of disease. It would be nice to know, okay, is there any relationship between age and the target, and sex and the target, and the resting blood pressure and the target, and blah, blah, blah. But typically doing that one by one takes a lot of time, right? But one thing, I usually don't recommend doing BI in Python, but there is one library that I would like you guys to take a look at, right? And so it's known as, so if you say Python, let's say plot pairs of columns. You want to plot every pair, right? So there's a library called Seaborn, and there's something called pair plot. Okay, so you can use pair plot. That would give you, you just say that pair plot and then all the columns you want, and then it'll create this grid of every column against every other column. Okay, so let's try that. Dot pair plot. Okay, so import Seaborn as SNS, and then SNS dot pair plot. And here, our data frame is not that big, right? But if you only wanted to look at it for a few columns, you just limit those. But let's just go with the entire data set here. It does take a little bit of time because it's plotting everyone against each other. But it gives you a quick view into how does each variable relate to every other variable. So while that's coming up, let's also set up another chart. Maybe we'll look at target versus the cholesterol is something that we know probably has some effect. Okay, so here you go. We've got the grid, right? I know this is kind of a dense grid, but the nice thing about this is that just one line of code gave us all of this, right? So if we look at the last column here, let's see if we can. All right, the last column, the last row here is target. So the y-axis is target, and these are all the other columns. You've got age, sex, CP, and all of that. So we want to see that you have the value of 1 at the top and 0 at the bottom. Again, you guys can expand this, do it on your own, and look at the relationships. But what we really want to see is, are the value is target 1 bunched up together on one side of the plot or the other, right? Which might tell us something. So, for example, target versus cholesterol. There seems to be, at target 0, that means no heart disease. You see people with similar levels of cholesterol. Even when the heart disease is high, similar levels of cholesterol, maybe a few more data points on the top. Similarly, when we look at age, right? Age, you see people, with who have heart disease are also all over the spectrum. It's not like only old people have heart disease. So this might give you some ideas on which features to pick, right, in feature engineering. Another nice thing about this pair plot is that you get to look at every variable against itself. So if you look at target against target, that gives you it's the histogram essentially, right? So it essentially saves this the identity point of this matrix um, for the histogram. So this is target against target, which tells you how many people don't have heart disease and how many do, and you see that it's a good balance. If you don't have a good balance, if you have very few people that have heart disease and many that don't, which is actually pretty common in healthcare or in finance, then you might need to do something else. So we'll talk about that sometime. Okay. So then if you also look at, let's see, age, right? Age. So this is age against age. So this gives you a distribution of age. So it's a little skewed to the right, which makes sense for people with heart disease, right? And then, resting blood pressure also somewhat, skewed to the left. And so this really helps you, prepare well for your modeling. Okay. All right. I just want to show you guys this because it's a nice chart. Trying to do this in some of the other even BI tools is not that easy. All right. So let's go ahead and now start to look at, okay, we feel like target might have something to do with cholesterol. It might even have something to do with age, but we can only see this, one by one, right? But we just want to maybe do one more round of BI here to see how does target relate to age and cholesterol. Okay, so that's a basic scatter plot. I'm not going to go into the syntax for that. I'll let you guys look at that. So that's SNS scatter plot. You can look it up. Seaborn is the library for all of this. The x-axis, I would like to show age, and then my y-axis, maybe I'll do cholesterol, and the color, I will label the ones that are the ones that actually have the disease or not. Okay, so what this is giving us is age versus cholesterol, and we've flagged everybody that has disease as orange, and then that doesn't as blue. So this, we're not seeing that. If we had seen a bunch of orange points on the top right, which means people typically who are older and have high cholesterol, maybe more susceptible, or if you see bottom right or top left, or maybe young people. But what we're seeing from this chart, if you look at it closely, is that we would have thought that as you get older, maybe you might be more susceptible. But what this is saying is that people with relatives, you see more orange here than on this side. So we may believe that, or we have reason to believe that, if you are younger and you have cholesterol in this range, which it would be considered a high range anyway, then you might be susceptible to heart disease, right? So there's a combination of age and cholesterol, probably. Lower age, higher cholesterol, which kind of makes sense. All right. So, but what type of model do we have to build for this now? Because our regression models aren't going to work, and we do want to take into account age and cholesterol and all of that. So this is where we are going into a different arm of the decision tree, right? Of our tree here. So we are going down this. So if our here we're saying that our target is discrete. We say target is discrete. That means we have 0, 1, or some small subset of values. Then we are automatically in the target is discrete. That takes us to what we talked about earlier, which is classification. Okay. All right. So within classification, we're going to do a few things today. So let's go ahead and quickly get started. We do have a few different models to try out. Okay. All right. So one of the most basic ones is called logistic regression. Okay? So maybe we'll start with that, talk about that a little bit, and then we'll go into the actual model. So what happens when we were doing linear regression previously? When we were doing linear regression previously, we were taking data points that were, like this, and then we were trying to draw the line. But what if now our y? So this is y, which is our target, right? But what if instead of it being evenly distributed, y's cannot take continuous values, but they actually can only take discrete values. That means they can only take 0, 1, or some few values. Then you will start to see values like this, right? You'll start to see some values here, and then you'll start to see some values here where this is 0 and this is 1. Right? You can't have values in between 0 and 1. So what type of, if you try to fit a straight line here now, right? If you try to fit a straight line, you might capture, there'll be quite a bit of error here, right? If you did your mean squared error. So that wouldn't be a very good idea. So a straight line wouldn't be a good idea, right? So basically what is done is that you fit a different type of a curve. You're still doing regression. It's called regression because you're doing curve fitting. So you're essentially trying to fit a logistic curve. So we know that this curve shape, this is known as a logistic curve. And we're just trying to fit a logistic curve. And why are we trying to fit a logistic curve? Because by doing that, if we fit a logistic curve and then we set a threshold, let's put that threshold here, okay? Let's set that threshold here. And if we set that threshold, then we'd be able to say, okay, I've fit this curve. Any value that is below this threshold, we're going to automatically, push it down to 0. And any value that is above this threshold, we're going to automatically push it up and call it, y equals 1. Okay. So that's essentially what's happening with logistic regression. I'm not going to go into further details, but the point here is that this is, we're doing curve fitting again, but we're just fitting a logistic curve, right? And this point of threshold is going to come back again. So let's go ahead and build that model and then see what we get. Okay. Again, I know this might be a refresher for some of you, but let's start with this and then let's try to make it better. Okay. All right. So let's build a logistic regression model. Go find out where that library is in sklearn. So it's sklearn logistic regression. It's in linear model, just like linear regression was, but it's called logistic regression. And let's see if we have. So there's many parameters we can set. Just looking at here's the example, loading regression, and then we're doing a fit and then a predict, right? So all of those functions steps we already knew. So let's go ahead and do that. From sklearn linear model, import logistic regression. And then remember we said define, fit, predict, and evaluate, right? So let's do that. MDL. Oh, actually we didn't specify our data, y and x. So let's do that before we do this, all right? So let's say we want y is the target column, and x is the data frame, except we're going to drop the target column. We're going to use all the other columns. And remember, we have defined whether it's a column or a row, so we're dropping axis equals 1 is the column. And then x train x is y. Train y test is train plus split x, y, and then we set our test size. Let's leave it as 0.2 like we always do, and then, okay, all right. So we've defined our target and our features to some extent, and then let's see, call model, it's called logistic regression for heart disease, logistic regression. This is our define, then we do fit, train, y, train, and then we're going to do our prediction, but let's save that as y test pred dot predict x test. Okay, so let's do this first, and let's just see if it runs. Okay, so it is trying to run it. Let's see. We've got our x train, x test, y train, y test. We've split x and y. Let's see if all right, let's go down here, model, fit x train and y train, and then we are trying to predict x test. Let's see if y not having the let's convert y from a column to a series in C. So Ravel typically does that. Let's see if that helps. No, that doesn't make a difference. Hold on. Let's see if this actually calculated though. Okay, it did calculate it. Okay, so this was some sort of a warning again. All right, so we've got our y test spread, but how do you decide whether this is a good result or a bad result? Remember when it came to linear regression, or when we were looking at continuous values, we were looking at the absolute error, right, between the target and the what we were our prediction versus the actual. We were looking at the difference between the two, and then trying to figure out whether minimize that error, either absolute or squared error or something like that. But the thing is, when we are dealing with binary or discrete values, we definitely, we won't be able to take the differences, right? Because the difference between a 0 and a 1 and a 1 and a 0, it's very, it's not going to give us a good idea of whether it's correct or not. So there is another way to do that. All right, so let's look at it, and that is known as, in this classification space, it is known as a confusion matrix. Okay, so this is a new term. Let's look at learn confusion matrix. So it's in dot metrics, and let's take a look at that. So model sklearn dot metrics is the confusion matrix, and you'll see what it does here in a second. So this is one that we could have gone and searched for it and looked for it, but interest of time, I'm just trying to do this quickly. So we give our y test and our y test spread just like we've done before. Okay, just like our errors. And so let's print that. Okay, so what do these values mean now? So it's giving us a matrix. So let's talk about that here for a bit. Okay. So in order to evaluate classification models, because we're not looking at just pure errors. So the values we got there where we had, let's see, so 20, 10, 4, and 27, right? So we had a value of 20, apologize, my pen is not working today. Try this again. Okay, otherwise I'll have to do this in Excel. Just give me 1 minute. Okay, there you go. All right, so we got values 20, 10, 4, and 27. Right? Those are the four values we got, and so this was what we got when we asked for a confusion matrix. And what this is telling us is that among the actuals that were, this is no disease. Okay, target is 0, and this is the person had the disease. So they were actually yes or no, right? That's versus what was the prediction predicted. Okay, predicted no and yes. Okay, so look at it as a that is called a matrix. And so the ones that we got right were, this was a set of people that actually had the disease, and we got 27 of them right. We mistakenly misdiagnosed 4 of them because that's what our prediction said. And then among the people that didn't have the disease, we correctly got 20 of them, but we missed 10 of them. Okay, we thought 10 of them actually had it when they didn't. All right. So now, how do we use this to tell whether? So it's easy for us to say, oh, the accuracy, right? We can say that the accuracy is. By the way, this is known as the. These are known as true positives. And again, I know this might bring memories to some of you guys. This is called true positive, and this is known as true negative. Okay, and this is this was negative, but it was false and got it wrong, right? So maybe we do that. This is a false negative, and this is a false positive, right? So we falsely predicted this person to be positive. We falsely predicted these people to be negative. Okay, so the accuracy we can simply calculate as the true positive plus the true negative divided, true positive plus true negative divided by the total, right? So we could say 27 plus 20 divided by the total number, right? So let's just go ahead and calculate that here real quick. we've got, I'm just bringing out my calculator here. So you have 27 plus, so you got 47 divided by the total is plus another 10 and plus another 4, 61. Okay, and so you got 47 divided by 61 gives us 0.77. All right, so that is our accuracy. But what's wrong with this? If we just looked at accuracy, the problem is that in cases where there's very few people who actually have a disease. So if in reality there was only one or two people that had the disease, so let's take a small detour here, and then we say, okay, suppose we had, suppose it was something like this, right? The number of people who actually had the disease is one person, and then who didn't have was 99. And then we said, you know what? The prediction was that nobody had the disease. And so you basically said that, everybody did not have the disease. Okay. So you predicted no for everybody. That was no. Right? So something like this, right? Or actually, yeah. So when you go down this path where you're saying that the actual people that had, it was 199, right? You predicted no for this, 99. And you predicted no for everybody. And so what happens is you would basically get an accuracy of 99 over 100, right? Because you didn't really predict that anybody had the disease. So you will get a 99% accuracy. But guess what? You completely missed the person who actually had the disease, right? So this is not a very good model. And this is what happens quite a bit in industry, especially in models like healthcare, fraud detection, and things like that, okay? So that's why accuracy is not always a good metric for when you're talking about classification, right? So now let's go back up here and then let's see what else we can say. So if accuracy is not the best metric, then what is the best metric? If we were to look at, what is among the people that were actually had the disease, how many did we catch? Okay, so if we did something like this, we calculated 27 divided by all the people that actually had the disease, right? 27 plus 4. So how many of the people that actually had the disease did we correctly predict, right? So this is 27 over 31, which is about 0.87%. 0.87, okay? Or 87%. And if we then look at the proportion of people that let's do the same thing up here. So we what is the proportion of people that we got right, that actually didn't have the disease, and we actually predicted them to not have the disease as 20 over 20 plus 10, right? And that is 20 over 30, which is 0.67. Okay. So this now, it would be nice, right? To make sure that these values are high, right? But if we were to, let's look at the false positive rate. So this is what we would call the true positive. Let me put that in a different color here. This is the true positive rate. The proportion of actually the right ones that we got right. Okay. And if we were to, so these are the ones that among the people that we didn't get. So if we erase this here, let's just make that, let's do that. Let's take the ones that we got wrong. Okay, so 10, we got 10 wrong out of the people that actually didn't have the disease, right? So 10 over 30, right, which is 0.3. All right, so this is the false positive rate, right? That means we falsely flag them as positive out of all the people that were negative. Okay. So, by the way, there's terms for some of these that you may hear. What we calculate on these columns, this is known as recall. You might have heard that before. And then you can do the same thing for these columns as well. Okay, and that's called those have their own names. But I won't go into all of that because it's the columnar calculations are called precision and these are called recall. But the point is that we know that the ones that we are getting right is a true positive rate, and the ones that we are falsely flagging as positive is a false positive rate. And what we want is, can we figure out whether this is, so if our true positive rate is 0.87 and our false positive rate is 0.33, is that good or not, right? That's the question. So we want our true positive rate to be, we want this to be high. We want our true positive rate to be high, and we want our false positive rate, we want this to be high, and we want this to be low, right? That's what we want. So any model that gives a high true positive rate and a low false positive rate is good. So how do you measure that? How do you get that? So this is 1 point. And remember when we talked about regression, you see this threshold here? So all these calculations are based on some threshold that the model has selected. But then what if we move that threshold? So let's draw out a curve here. So let's put this curve together. Okay, and we're going to do let's put our false positive rate on the x-axis and our true positive rate on the y-axis. Okay, so in this case, and they're both between 0 and 1. Okay, between 0 and 1. So this specific one has a value of 0.87 for true positive. So somewhere here, close to 0.9, and the false positive is 0.3. Okay, so somewhere here. This is our point, right? Okay, this was from just one of these, but what if this threshold was down here? What if this threshold was brought down? What if you brought that threshold down some? What would happen? If we brought that threshold down to this point, right? Some of the points that were up here, that might have been up here, might have gotten, although they may actually should have been 0. Y should have been 0 for them, got squished and pushed up here just because we brought this threshold down. Remember that threshold is the point where we're trying to push points to the bottom or to the top, right? So if we brought that down, then we would see that our true positives, as our threshold goes down, our true positives might go down, but our false positives also might go down, right? So you might end up with some point, lower true positives and lower false positives. Whereas if we move the threshold up, let's say we push this threshold, all the way here, somewhere here, then we're going to capture all the zeros are probably going to be fine, but we're going to miss some of the positive values, right? So in this way, you're going to, by moving this threshold up and down, you're going to be creating something like this, right? You're going to be creating these points. And of course, when you move the threshold all the way down, you're going to be missing everything, right? You're going to be completely off. So if you brought it all the way down, if you brought this threshold down to 0, then it's going to push everything to be positive, right? So your false positive rate is going to be 1, but your true positive is also going to be 1, right? Because you basically said everything is positive. And then if you're, brought this threshold all the way to the other extreme, both are going to be 0. So by moving this threshold around, you will end up creating a curve that looks something like this. Okay, and it always has to end in 1, 1 and start in 0, 0. So what does that give us? So by playing around with this or changing the threshold, we created this. The more that this threshold separates the set of points on the bottom here from the ones on the top there, the more it separates them out, the more you will see this curve, scoot to the end like this. It'll go closer to the edge because you're able to increase your true positives without increasing your false positives much, right? That's what a good gap here would give you. So that means that the more the curve looks like this, the better, right? But how do you mathematically capture that? So what we do is that if you look at this as a square, the area of the square is 1 times 1, right? Which is 1. So if we looked at the area under this curve, the closer that area is to a value of 1, that means it is able to get a good and nice high positive, true positive rate without increasing the false positives much. Okay, so this, that area, right? First of all, this curve, again, terminology, this curve is known as a receiver operating curve, right? Or ROC. Again, they like to use acronyms. And then this area, so the area under the ROC curve, right, is also known as the AUC score. Okay, so the AUC score is basically this area under this curve, and so we basically want that to be very, very close to 1 or as high as possible. Okay, so it's a long explanation, but I really wanted you guys to understand where does this AUC come from, right, and what does it mean? Because this is typically not covered very well out there in the textbooks or even in a lot of the videos. All right, so now that we know that we want an AUC score that is high, and by the way, if you ran a model and then you saw something like this, you had a curve that went straight up like that and straight that way, that means your AUC was actually a value of 1, something's wrong with your model. Okay, that's not realistic. Either your model basically has an exact solution, which means you don't need machine learning for it, or most often what happens is one of the features, one of the columns you're using as a feature is actually an output column. So imagine that you had another column here that said, if they had the disease, then target and then something related to the target, and then you were using that as a feature, right? So you would go back and remove that because you're not going to have that in data, and then rerun it to get a more realistic model. Okay. All right. So having said that, now let's go ahead and just run the ROC, calculate the AUC value, and then see what we get. All right. So we get these values from the confusion matrix, but we already also have the AUC score. That is called I think it's called the ROC. Yeah, ROC AUC score. Okay, so you'll say print ROC AUC score between Y, S, and Y. Okay, so this is what you will be using. ROC AUC score is what you'll be using for all classification types of models. All right, so we do have quite a bit more to get through today, but so having said that, now we've got our ROC AUC score, yeah, and what's a good ROC AUC score? Or let's just call it AUC score. A good value is, typically from projects we've done, I think, I would typically accept something with, anything more than a 0.75 or so or above, maybe even go down to 0.7 if the data is still small. But it's nice to have values, 0.8, 0.85, or 0.9 or above. Okay. Again, that's not a rule of thumb. It's just kind of what we've seen from projects. In certain projects, you really want it to be very, very high. If it's something that like facial recognition, you're not going to want to have errors with that. Okay. So this is one of the models that we have talked about. We have logistic regression. But then we also have, if we, we have another type of type of model here, which uses probabilities. Okay, so let's talk about that here. That model is known as the. So first of all, if you've already got this, why would you bother doing another model? Well, whenever you're building models for these, typically you would want to evaluate different types of models to see which model is able to capture the relationships better. Okay, sometimes maybe fitting a logistic curve might not work very well, but another method might work better. So some of these you actually would have to run them in parallel to see which one does better. Okay, so another model is known as the naive Bayes model, and this is a very popular model because it is very easy to explain. Okay? The logistic regression model is also good. It's very easy to run, but the naive Bayes is very easy to explain because it is based on probabilities. Okay, so some of you have taken probability and statistics, and you might remember the Bayes theorem, right? So let's see if we could. Maybe let's do an example first, and then that will give us a way to do this. Right. Okay, so let's just talk about Bayes' theorem for a minute. So you guys remember that if you have, so Bayes' theorem basically says that if I want to know the probability that I should, probability that an event A is going to happen, given that I know that B happened, right? Then this is the probability of A and B divided by the probability of B. This is just the definition of conditional probability. This is conditional probability here. But then I also, if I do the same thing for B to A, that is probability of A intersect B divided by the probability of A, right? So since these two are the same, I'm going to replace this here, A intersect B, with probability of B given A times probability of A over probability of B. Okay, so this is known as Bayes' theorem. So Bayes' theorem says if I know about some event, if I know probability of B given A very well, suppose I know that, and then I can figure out the probability of A given B, which is harder for me to figure out, just by multiplying this probability times the probability of A divided by the probability of B. Okay, so why is this helpful? Think about it. If I want to know the probability that somebody has a disease, given that they have, high cholesterol, right? This is something I want to know. But if I am able to look at the data and I am able to tell of the people that had the disease, how many of them had high cholesterol? So we're looking at the reverse. So we look at the data, we look at all the people that had the disease, and then what proportion of them had high cholesterol. Okay? And then I can multiply that with the probability of the people that had the disease, and then I can, divide that by the probability of people that have high cholesterol, and then that essentially helps me to figure out whether I can calculate whether in general, if somebody has high cholesterol, what is the probability of them having the disease. Okay, this is the fundamental theory behind the naive Bayes theorem. Okay, so let's go ahead and apply that here for this example. All right, so look at this. I've basically taken the data set, a small snippet, and I've modified it just to make this easy, and then we'll run it overall. So let's say that we're only looking at 10 patients, and we've broken their ages down. I just made this a little easier. So either they have they're older. So let's go to the first row. This patient is high in age. That means they're an older person. It's a female. They have a high resting blood pressure. They don't show any signs of high cholesterol, and their heart rate is high. This person's heart rate is high, and this person did not have the disease. Okay, and then every row. And now a new case has come in here down here. I have a new patient that is low in age, so a young person. It's a male. The person does not have high blood pressure, mild cholesterol, and does not have a high heart rate. So, and the question is, we're trying to figure out the answer to this, right? What is does this person have the disease or not? So let's use Bayes to try to solve this problem. You see that this is a very probabilistic centric problem. There's really, what is machine learning about this? And I'll show you that here in a second. Okay, so the first thing we're going to do is we order the patients into yeses and nos. Okay, so I just put all the patients up top here that have the disease, and at the bottom that don't have the disease, just for ease of calculation, because we're going to do this manually, right? Okay, so let's now create a small table here. Let's create a table here. So we'll say age and high, low, average, and then say sex is male or female, and then we've got high T rest yes, and then that is either yes or no. Then cholesterol, say strong, mild, or none. And then I heart rate and that the yes or no. Okay. All right. So we have this. I'm going to create this table here. And so these are my features here. And these are the whatever classes we have for them. Okay. So now I'm just going to group them by yeses and or who was the target that they had the disease, or target is that they didn't have the disease. Okay. Actually, let me write that slightly differently. Let me just put Y and N here. So first of all, if we were just to look at, what is the probability of Y? The probability of Y here is that you've got 1, 2, 3, 4, 5, 6 out of 10, right? So you've got 6 out of 10 is the probability of people that have the disease, and no is 4 out of 10, right? All right, so we've got that. Now this is the probability. Now, out of all the people that have disease, let's look at all the yeses, okay? Out of all the people that have the disease, how many of them have a age high? So we're looking at this set now. So 1, 2, 3, right? So 3 out of 6. Remember, we're looking at this subset and how many of them had a high age. Low is 2 out of 6 and average is 1 out of 6, right? You see what I'm doing here? Okay, and then we do the same thing for male and female. You've got 4 male and 2 female. Blood pressure, we've got 3 yeses and 3 nos. So remember, you see what we're actually doing here is we're essentially calculating these values, right? Given the disease, they had the disease, what is the probability that they had some feature? Okay, that's what we're doing here. All right, then when it comes to cholesterol, you've got 2 people with none or strong, 2 with mild, and 2 with none. And then heart rate, we've got 2 yeses and 4 nos. Okay. All right. So we've got all of these probabilities, and then we could do the same thing for the nos. Okay. I'm not gonna do that here, but let's see. So what do we do with this now? What with these probabilities? Well, we are saying that. So what we're saying here, remember we said the probability of disease, or let's say Y target equals Y, given some X, okay, which is my features here, is the probability of X given target equals Y times the probability that target equals Y, right? Divided by the probability of X. Yeah. So this is Bayes' theorem. So now notice that when we are writing this down, okay, how do we estimate? So probability of X given target Y, that's these values, right? 3, 6, 2, 6, 1, 6. That's all what we have. Now let's take a look at our new case. Our new case is Our new case says that the age is low, so let's mark, so you get this, they're low. Male, no for the third feature, that's mild, and then high is a no, right? So now that we have all of these probabilities, right, we should be able to put them together, and then we already have our target is, probability that the target is y, right? That is this value, right? That is this here. That's what goes in here, and then the probability of the x's, right? So let me write this down for you here. Bring that up. So let's write that down. If I wrote this down, target is, this is for target is yes, right? Now if I do this for probability that target is no, given x, right? Same thing here, probability that x given target is no times probability that target is no divided by probability of x. So now we have this one equation and this second equation, right? So if we have been able to calculate each one of these, right, we know that both of these are divided by the same value, probability of x, right? Which we don't have that, right? We don't have the probability of x. But if we take probability, right, that the target is yes, okay, given x, so basically our first equation, and then, so if this value, if the first equation divided by the first plus the second, so we take this probability that the target equals y, given x, and the probability that target is no, given x. If we were to calculate this ratio, right, we know that you have a probability of x denominator here and a probability x denominator here, which means both of them get canceled out, right? That means this ratio will be probability that x given target equals y times probability that target equals y divided by probability that x given target equals n times probability that target equals n, right? So this is the ratio because the probability of x's cancel each other out. So if we calculate this, okay, if we calculate this, we know we have all these values from this table up here. And if this value is greater than 0.5, right, or you can take the numerator is greater than the denominator, then we know that we should assign a value of target equals yes. Otherwise, we should assign a value target equals no. Okay, so let's just finish out that example using this calculation. So let's do probability that of x given target equals y. Okay, that means the person had the disease. That means among the people that have the disease, what is the probability of x? So that is 2/6 times 4/6, 2/6 times 4/6 times 3/6 times 2/6 times 2/6, and that comes out to 0.014, okay, or 0.015, put it that way. And then the probability of x given target equals null. So if we had done this column, actually, let's just do that. At least one of them real quick. So among the no's, there's no, you see there's 2 high and 2 averages. So you've got 2 out of 4 and 2 averages, but 0 for this, right? For this new person, this person's age is low, which means it's a 0. So we can go ahead and calculate all of these values, but if one of them is a 0, anyway, the product is going to be a 0. Right? So we could go ahead and do all of this, and we would end up with a value of 0. But it could very well have been some other probability, right? And now what we do is, so we have this probability for yes and this probability for no. So we take 0.015 divided by 0.015 plus 0, right? And this value is greater than 0.5. It's actually equal to 1. So we say that the person, in this case, the person has a likelihood that they have the disease. Okay. So we're saying that target equals y. Okay, this is the prediction. So hopefully that kind of gives you an idea of what is happening behind the scenes. It is a purely probabilistic model. Now, one question that comes up is how come you can just multiply these products whenever you are trying to, so this is probability of age given y, probability of sex given y, probability. And in order to calculate this is an approximation. This assumes independence. It's only when they're independent can you multiply this. And that assumption of independence is why it is called naive. Okay, so you are being naive by assuming independence between these events. Okay, so yeah, you go ahead and calculate the conditional probabilities, and then just by taking the conditional probability value for each one of them and taking the ratio of them. So let's say that this was not 0 and it was 0.05 or something like that. Then the ratio of 0.015 plus 0.05, that would have been less than 0.5, which means it would have said, oh, you know what, there's a higher likelihood that this person does not have the disease. Okay, so I'm just gonna undo that here. All right. Okay, so let's now go ahead and apply naive Bayes to the same problem. It's a very probabilistic model. It comes under machine learning because they're just algorithms to do it, but there's nothing else machine learning about this model. This used to be a very popular model in the past before neural networks kind of came in and started becoming more popular. But I still very much recommend using these models because they're very easy to explain and they're very realistic. Okay. All right. So let's quickly go ahead and build a naive Bayes model. Let's look for that. SK learn naive Bayes. That's the math behind it. I know I went in a little bit more into the math on this one, and the reasoning was because it is purely based on the Bayes theorem, and so you should be able to calculate this. You don't even need to use these libraries. It just so happens that they have libraries. So okay, so under sklearn, there's an area called .naive Bayes, and then there's this Gaussian NB, and everything else is the same logic. So let's copy this code here. dot naive Bayes, and then Gaussian NB. All right, this is what we normally do. Let's focus naive Bayes Gaussian. Okay, and now let's go ahead and print the ROC AUC score. We know that that's what we would be using to compare the models. Right. Okay, so it's slightly better, 0.769, almost the same, not very different. But this would be the naive Bayes result, and there's a few other types of naive Bayes models which are slightly different. So this one, the Gaussian one, basically assumes the normal distribution for calculating some of those probabilities. But there is one called the Bernoulli model, which basically converts some of the features into binomial. Let's just run that to see whether that gives us anything different. This would be Bernoulli. The nice thing about Bernoulli is that it does some pre-processing, so the features are a little bit better. Okay, let's call this. This is the Gaussian. The mathematics is still exactly the same. So I usually run multiple of these just to okay. And the reason that I actually change the name of the model every time, even though I'm just rerunning the code, is whenever we want to save the model later, we want to remember we're actually going to save it by this name. Right? That's why we keep changing that name. Okay. All right. So the Bernoulli naive Bayes gives a lower score. Sometimes it helps to turn on the binarize feature. Okay, so when we turn on binarize, it brings it up a little bit, but this Gaussian naive Bayes was already good enough. There is one more. I'm not going to go into that here in the interest of time. Let's start with it and see if we are able to. Okay, so there is another one called the multinomial naive Bayes, and what this does is instead of binarizing it, we actually go into multiple levels of. It converts every column not just into a binary, but into multiple levels. So it is a slightly more sophisticated model. Let's try to run that here. See, we might need some more pre-processing for that. Let's look for what is it called? Multinomial here, naive Bayes, and let's see. Okay, so this cannot binarize, of course, so it doesn't know what to do with that. Okay. All right, so this one, so multinomial gave you a lower score. So the best one is the Bernoulli. But sometimes these it requires all the values to be non-negative. Okay, so you might need to if you do see that, you'll have to do something called scaling. We'll go over this sometime. How do you scale your inputs to get better results? Okay. All right. Finally, we can now go. We'll do one more model here in the last few minutes, and just for completeness, this is one of the most popular models out in industry today because it uses a different concept. So let's go into this. This is called the support vector machines, and you guys have definitely heard about this before. But what makes it different? The question is what makes it different, right? So let's go here and okay. So when we're talking about support vector machines, first of all, why do we care? We already have enough models, right, to deal with. We already have a logistic regression. We have naive Bayes. We have all of these. So why bother? Um, well, it just so happens that that logistic regression, okay, logistic regression uses probabilities to figure out that to fit this curve, and then to set these thresholds and to go beyond these thresholds. So logistic regression is a probabilistic model. Naive Bayes is, of course, definitely probabilistic. So you have these probabilistic models, but in these data sets, if you have anomalous data, a lot of anomalies, then it will throw all the probabilities off, right? Whereas what support vector machines do, okay, so suppose you have, let's put all of our, so you have, these are the points of, somebody having a disease, okay, and these are the points of somebody not having a disease. So what the support vector machines would do is it creates it tries to create a boundary, okay, that so it could draw a boundary like this, right? It could draw a boundary between these 2 points, kind of like that, by trying to get all the points into one, or it could try to draw it, like this, right? But it tries to draw the line. So it says, okay, I could do that and I could do that. But what I will do is I'm going to draw a line that I'm going to draw a line this way because it creates the biggest gap between the two clusters, if you want to call them clusters. Yeah, we know that there's some points on this side that should be on that side, and there's some points on that side that should be on this side, and all of that. But we're going to assume those are anomalies. So we're going to assume this is an anomaly. We're going to assume this is an anomaly. And now we can draw this very clearly, that clearly separates out one from the other. Whereas the other models, they can't differentiate between anomalous points and the others, okay? So essentially it is trying to create this, or it tries to create a boundary that that shows the largest the largest margin between the classes. Okay, so it tries to maximize the gap between the one class and the other class. So that's all I'm going to say about support vector machines. How does it do that? Well, it's a mathematical optimization problem. I mean, of course, it doesn't know that, what should be an anomaly, what shouldn't be an anomaly, but it basically iterates through so many of these different boundaries and finds the one that has the biggest gap, even though, some of the points might be on either side. Okay. And think about it from a realistic perspective. That is what we would probably also do, right? Knowing that some of these data points might be anomalous, we would try to draw a boundary that separates them out as best as possible, but without trying to overfit and trying to avoid some of these ones just because they're flagged one or the other, right? Okay, so that's essentially what support vector machines do. The reason you use support vector machines, again, is whenever you have data with anomalies, then it would be a good idea to use SVM. So let's go ahead and look for sklearn SVM. Um, and that is, you could do a support vector for regression also, but we're going to do it for classification. Okay, so under .svm, and then we have svc. So let's do this. svm, and let's import svc. Right, so this is svc, and fit, predict, and then see what we get here. All right, so in this case, our SV support vector machine model didn't really give a very good result. Again, the lowest value that an ROC is ever going to be is not 0. Remember that if we go back to our chart, our ROC chart here, the worst that could happen is that it's going to have, the line is going to go through the middle, okay? That means that you were terrible at predicting, the true positive or the false positive. That's as bad as it gets. So the value of the area at 0.5 means it doesn't get any worse, right? That means you really can't predict it at all. So anything that's in that 0.5, 0.6 range, it doesn't mean much, right? You really have to get over the 0.75 or 0.8 kind of range for it to mean something. So going back to SVM, if this is 0.55 is all it can do, of course you got to go and modify some of the parameters and all of that, but you might be more successful modifying parameters for naive Bayes in this case to be able to do better. But all of these, so there's some things that we didn't talk about today. We'll talk about next time. In terms of scaling the data, right? We see data points here. Some of them are in values 0, 1, some of them are hundreds. So it would help to scale the data points, right? And so scaling of the data is a critical step that we'll talk about next time. It really would make a difference. But in general, we've gone through the different model types here. And just a comment here, anytime you are dealing with healthcare data, then it really, naive Bayes models are very, well suited for that, because we know that they are inherently, there might be dependencies between each of the columns, but it's possible to have people that have something high of one and low of another. And these models tend to do well for healthcare types of data. So you don't want to miss naive Bayes in dealing with these models. The other thing that we've learned today is that when you are doing classification models, then you don't want to use error as a method of evaluation. You really want to use this, the true positive and false positive rates. And you want to use this curve, and so the area under that curve is a decently good metric to see whether your models are doing well or not. Naive Bayes leverages Bayes' theorem, and it's a very simple probabilistic model. It doesn't typically require any type of learning. This is just pure calculations. It just happens to be that there are good algorithms that do those calculations for you. And then finally, support vector machines are good whenever you have data with anomalies. Another space where naive Bayes works well, or where you have anomalies. Let me put it this way: where you have anomalies, or if you only have 1 or 2 data points where the target is 1 and all the others are 0. So one example, disease might be 1, but financial data like fraud detection is another one. You might only have 1, case of fraud among millions and millions, and so that is where you really want to use models like naive Bayes. You may use other models that we'll talk about in future, but you definitely want to use the AUC to be able to tell you whether you're doing well or not, because then it would ding you significantly if you flagged somebody as not fraud who was fraud, right? As opposed to using simple accuracy. All right, guys. So that is the end of the session for today.